Hi ladies and gentlemen, this is Mr. Green. This is another in my series of recordings for pre-cal. What we're looking at now is 8.3. Okay, we've done inverse trig, we've done solving equations, so I want to make certain we see why we might want to be doing this. These are some applications about harmonic motion. Okay, so the movement of a weight on a string, the amplitude, that is the coefficient in front of the trig function, tells you the height, both up and down, of that movement that might be of that weight on a string. The frequency, that is the value inside the parentheses. Remember that? Remember radians and stuff like that? So you got this swinging back and forth, and you shorten the string and it swings faster. Okay? The period is 1 over that frequency. Cool? Okay. Let's move forward here and look at some real examples. A clown is rocking in a rocking chair in a dark room. The glowing red nose moves back and forth a distance of 0.42 meters, exactly 30 times in a minute, in simple harmonic motion. What is the amplitude of this motion? Well, it's really not that difficult. They're giving it to you right here. They're telling you that it's moving 0.42. So from here to here is 0.42. Guess what? If it's harmonic motion, then the amplitude is going to be half of that value, or 0.21. I wrote that very poorly. I'm using my mouse. You can tell. 0.21 meters. That would be the amplitude of that motion. So you'd be looking at something like 0.21 meters, I'm sorry, 0.21 sine of some function, okay? Because it started at 0, it started in the middle, and started rocking back and forth. And it might be an inverse sine, but you'd have to look at it and see what it looked like. But essentially what it's going to look like is this type of a harmonic motion like this. Okay? And what are we talking about? Well, from here to here is that 0.42, okay? And you're talking about this being 2-1. That's what you'll be looking at, okay? Now, it does it at 30 times in a minute. Well, that means he's got this and this and this. Okay, what is the frequency of it? Well, 30 times in a minute, that means it's getting 1 every 2 seconds, right? So that's what your frequency would be, 1 every 2 seconds. Cool? Do you see how we're applying these things? A child swing, sitting in a swing set, swinging back and forth, just a swinging, right? A child swings on the playground with a 2.5 long chain. What is the period of the child's motion? What's the frequency of the vibration? Well, the period's really easy, okay? For a pendulum, you say that T is equal to 2 times pi times the square root of the length of the chain divided by the gravitational constant. Okay, so it's 2 pi square root of 2.5, where'd I get the 2.5? Right here. That's how long the chain was. Divided by 9.8. 9.8 is meters per second. When you work all that out, you get that the period is 3.1735 seconds per swing. About 3 seconds per swing. Okay? So what is the frequency of the vibration? You take 1 divided by t. You take 1 over t. So you take 1 over this, and it's about 0.315 megahertz. Not megahertz, hertz. 0.315 hertz. That's seconds per swing. Okay? Cool. Well, that's not that difficult. Okay, this is beginning to sound a little bit easier. So we've got a pendulum with a mass of 1 gram. It was released. The string made an angle of 7 degrees with vertical. The bob of the pendulum returns to its lowest point every 1 second. What is the period, the frequency, and the amplitude? Well, not that difficult again. What we're going to say, the amplitude is 7 degrees. I mean, it's telling you right here, it's going up 7 degrees, right? And it's going to go back down to 0 and then back up 7 degrees. It's telling you right here that it's 0.1 seconds, 1/10 of a second, right? So the actual frequency of it is going to be 2 seconds. You have to go from top to top. Okay? And if you take 1 divided by 0.2, you get 5 hertz. Cool? So, if this pendulum was set to keep time, and then they shot it off and landed it on the moon, gravity is 1/6 the gravity of Earth. What property should have to change to make sure it kept the same accurate time? Well, remember, we were using this gravitational constant here. Where is it? Oh, we were taking the length divided by gravity, right? I'll go back up here a couple slides. Right here. Length divided by gravity. That's where we were getting this uh, period, right? So if that's what we're using to get the period here, and we got 1/6 less gravity, that means we need to increase the length on the rope by 6 times, by a factor of 6. It has to be 6 times longer. That's the easy way to looking at that problem. Okay, and this was just a brief introduction to some applications. You're going to do similar type problems in the practices and in the quizzes. If you have any questions, make certain you bring them to Class Connect or to the tutoring sessions on during the week. I look forward to seeing you there. Talk to you later. Bye.